Good morning. We are back to looking at electric forces, electric fields, and as I keep repeating, I talked about in the previous lectures, that there's a lot of stuff in chapter 21. So don't panic, just be persistent. We'll get through all of this stuff. We do have one more lecture looking at chapter 21. So we're going to wrap things up today. So we had introduced the idea of an electric field, and now we want to introduce an idea of what are called field lines. We can actually draw lines that are keeping track of the orientation of the electric field around positive and negative charges at each location. So the idea with this is electric field lines are directed away from positive charges. The electric field lines are directed towards negative charges. The number of lines that we draw are proportional to the amount of charge. So the pictures we have right here, if this was a diagram that we were using, we would say, oh, the electric charge of the positive and the negative charges match because we're using the same number of field lines to represent them. And then what we do is, this becomes the artistic part of the course, is we can take the electric field lines that originate, we terminate them on the surface of these charges. So this is where this field line attaches to this, and then it can be directed and matched up with this one. And that says that between the two charges, the electric field is consistently in that direction. Now, what should I do with this electric field line? Because that negative charge has its own electric field line directed towards it. What I'm going to do is, very artistically, I am going to draw a curved path connecting those two, and then I'm going to do the same thing with this. And then this sounds wild and crazy, but I'm going to take these lines and connect it with this one. Now there's a couple of lines that I can't really turn this one to one side or the other. This one electric field line I'm just going to allow to head out infinitely far, and the one on the negative charge too, but the other ones can all be connected. And so what this does is, what we've noticed is that the electric field line, the electric field calculations get real complicated really fast, right? The point charges were pretty straightforward, but then I added some more point charges and we had to do vector addition. And then we did integrations, and that was absolutely terrifying. And so, is there a way that we could just, with our understanding of how these electric fields are related to the charges, could I just use that to draw some lines in that would approximate? And that's what the approach of electric field lines does for us. So what I've done is I've got a positive charge and a negative charge, and I want to find out what the electric field is right there. And I think, oh no, that's going to be an absolutely terrifying, horrendous calculation. Can't I just do a drawing? And so that's what field lines allow us to do. So if you'll notice, these are representing the same amount of positive and negative charge. It's actually what we call an electric dipole. Two charges, 2 point charges, one positive, one negative, but they have the same amount of charge. This is a model that's used a lot for molecules, and we'll see some examples for that. So 2 point charges, positive, negative. I know that they have the same amount of charge because they have the same number of field lines, right? And so notice what we've been able to do is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They've used 10 lines. They've been they're supposed to be evenly spaced. They didn't get them evenly spaced along the surface. And then I just start connecting lines artistically, and that's it. So that says that, yeah, at that point right there, the effect of that positive charge and negative charge is to create an E field in that direction. And an E field in that direction tells me if another positive charge comes wandering by and ends up at point P, and we let go, it's going to experience a force in that direction. In fact, it's going to experience a force even if we hold on. So if I hold on to the charge, it's still experiencing a force. If it's a negative charge, the force will be opposite. And that's kind of funny, because let's get to a point right here. If I placed a charge, a positive charge right there, what would the direction of the net force be? And I don't want to do all the calculations. I don't want to sit down and, so what I can do is I can draw this field line diagram, and it says, oh, the field would actually be directed to the right. And that says if I placed a positive charge there, at least initially, the force on it would be pushing it in that direction. And then it's going to start moving, and we have to recalculate every time it moves. But as long as it's at that location, the force on it would be there. Now, how am I getting a force in this direction? Because my two charges are down here. Well, the negative charge is attracting the charge directly here. The positive charge is repelling it. So it's getting a repulsion force and an attractive force, and vector addition of those two forces is directly to the right. You go, oh, that's interesting, that's so cool. We could have done that with some diagrams, which we could have, and then these field lines are just a step beyond that in using diagrams to figure out what's going on. Similarly, let's say that we've got a couple of plates. Now we're gonna make a lot of use of this diagram. So I got a couple of plates. One has been positively charged, one's been negatively charged. We use this in different devices. If you have, certainly if you've taken chemistry or maybe some biology courses with labs, with laboratory equipment, we often have beams of things that are beams of electrons, for example, that are being accelerated, or mass spectrometers that are accelerating molecules. And so we're using, for those examples, we are using electric fields to bring those objects up to speed. So we're using electric fields to bring the objects up to speed, and we use this with charged plates. So one of these plates gets charged positive, one negative, and what that does for us in the central region is it creates an electric field that's approximately, again, this is a bit of an approximation, but it creates an electric field that's approximately uniform. So that's a really handy geometry to work from. And the field lines predict this. So the field lines are saying, look, if I have kind of a uniform distribution of positive charges and negative charges here, the electric field lines are going to be directed away from the positive charges towards the negative charges. So I'll start with a series of electric fields directed away from the positive charges, and they got to terminate on, equally spaced locations on that negative plate. And that's kind of like done. That's my diagram for what the field will look like. Okay. Now let's talk also a little bit about electric fields within conductors. So what we've got here is, I think it's a sphere. So it's a hollow sphere, and this is made out of some metal, maybe it's an iron sphere or stainless steel or something. And it's in a region where it could be exposed to different charged samples. And so I'm going to take a sample that has charge on it and place it at the center. What the field line approach tells us is that these electric field lines are going to be directed away from a positive charge. What happens when the field lines reach a conductor and they terminate? Because what happens within the conductor is, if this is positive, the electrons inside the conductor go, oh, wait a minute, I feel an attractive force. And the electrons that are in here begin migrating to the inner surface, but then they get stuck, because they get to the surface, and there's all these other nuclei and electrons holding them in place. So they can't necessarily leave the piece of metal, but they go to the surface and they get stuck there. What that creates is a negatively charged surface. There's a surplus of electrons along the surface. Well, those negatively charged electrons terminate the electric field. So it's not an infinite number of electrons that accumulate there. The number of electrons that find themselves at that inner surface will be just enough to match the value of Q. So what's going to happen is at the inner surface there will be an excess of electrons of total charge minus Q surrounding that inner surface. Within the conductor itself, once things settle down, there's no electric field. If there were an electric field in a conductor, then the electrons keep moving. So the electrons will just keep moving until all of the electric fields have been canceled out, and then the electrons stop moving. And they maintain a configuration, in this case, negative charge on this inner surface. Well, that's going to leave the outer surface to be positively charged. I need kind of neutral, a neutral region in between. So I get this charge build up on conductors. All of the charges end up on one of the surfaces, either on an outer surface or an inner surface of a conductor. Okay, so that's a way that, without doing any math, we just kind of reason our way through, I guess is what we're saying here. We can figure this out. A second item, also, which is kind of interesting, is that if I have a conductor, the E field at the surface has to be perpendicular. If it has any lateral components, let's say that there's an electric field along the surface, well, an electric field along the surface would make the electrons move. Opposite the direction of the electric field, but it would still make those electrons move. So once things have settled down on a conductor, then all the charge, any excess charge, has gone to surfaces. The charges at the surfaces are exactly what's needed to balance the presence of any other charges. And the electric field within the conducting material itself, away from the surfaces, is zero. And then the electric fields, where the electric fields make contact with the surface of a conductor, this is at a perpendicular angle. So that's interesting that we kind of reason our way through that. So what that says is, let's say that we have these big plates that are charged, so we're going to get these enormous electric fields. Is it going to be safe to walk into that region, or will we be exposed to these electric fields, which you can actually tolerate some pretty large electric fields? If you go to really high electric fields, then you could start to ionize things. But so let's say that we've got this electric field set up. What would happen if we have a container that's also a conductor, and we place it in the field? So, okay, so maybe this is a lightning storm happening, and this is me inside my car driving along, and all of a sudden there are these bolts of lightning that's set up. Am I going to be safe inside my car? And you go, yeah, because all the electrons will adapt very quickly. The electrons will be drawn to the surfaces or pushed away from the surfaces in a manner where the electric field inside that conducting material is going to be maintained as zero. So not only is the electric field within the conducting material itself zero, but if there's no other charges within this, then the electric field inside will also be zero. Okay, all right, this is an important topic, so let's pay attention on this one. The force acting on a charge in an electric field is given by F equals Q times E. That looks a lot like F equals mg, right? Back with gravitational fields, we said that the gravitational force was m times g. But now the force is going to be Q times E. The mass has been replaced by the charge, and the electric field, the gravitational field, has been replaced with the electric field. So here we go. We've got those plates set up again. We have this uniform electric field set up. Let's see what they're telling us. They give us the mass of the electron. They say there's 1.5 centimeters between the plates. So what's going to happen is we're going to generate a beam of electrons. So for some device that we're going to use to measure properties of whatever, we're going to get a beam of electrons, and that beam of electrons is going to be, we're going to get with electrons basically at rest. We're going to ionize some molecules and separate off some electrons, and then within this electric field, those electrons will start picking up speed. Once they leave the region between the two plates, then they just go into constant velocity. So this is a bit of an approximation, but if we treat the electric field uniform inside, but the electric field out here is basically zero, then there is an acceleration region between the two plates. Once it gets past the plates, the electron is drifting. So here are the numbers. They say that within the plates, we've generated an electric field. It's 20,000 newtons per coulomb. The distance that the electron will travel between the two plates is going to be given by 1.5 centimeters, 0.015 meters. It's going to start from rest. So let's assume it starts from rest. The mass of the electron, 9.11, 10 to the minus 31 kilograms. The charge of the electron is little e. So we've been using this little e as a symbol. And little e corresponds to 1.60, 10 to the minus 19 coulombs. Now, that's different from the little e that's a symbol that represents an electron. So like right there, I put a minus sign to remind me that's a symbol for the particle. This is actually a numerical constant, little e. So what I'm going to do is say, okay, the acceleration that the electron experiences depends on the force divided by the mass. Now, since it's an electric force, we can represent that in terms of the charge times the electric field. So I'm going to take Q times E and divide it by M, putting all those numbers in, keeping all the units standard. I'm getting an acceleration that is 3.5, 10 to the 15. 10 to the 15, it's another one of those enormous numbers, but yeah, this can happen over these short distances. Let's run through and see how these numbers develop. So this is the acceleration I'm getting. It's enormous, and that's because the force is reasonably large compared with, oh my gosh, the electron mass is so tiny. So we're going to get a constant acceleration as long as the force remains constant. So if the electric field is constant, and we're going to assume it is constant over that short distance, then during that short distance, when the electron's traveling, the acceleration will be a fixed value. And so that gives us the constant acceleration. We can use formulas from constant acceleration. The v naught was equal to 0. I'm solving for what will v be once we've traveled 1.5 centimeters. And that worked out to be 1.03, 10 to the 7 meters per second, or about 3% of the speed of light. Okay? And if we get close to the speed of light, we realize the formulas we've been using for kinematics won't work anymore. They'll give us incorrect numbers. We have to use special relativity, which we will. Later in the course, we'll learn about relativity so that we could do these sorts of problems accurately. But for now, we're just going to use constant acceleration formulas because the speeds, it's not too close to the speed of light. Okay, but you can see these electrons picked up this speed, and then once the electron is outside of this region, that's just going to become a constant velocity. So there's this short region of acceleration, and then there's this much longer region of drift. The electron is just maintaining that speed. What would happen if, instead of an electron, it was a proton? Well, the first thing that would have to change is we would have to reverse the charges on the plates. Before, we were using a negative charge plate and a positive charge plate to push on the electron, but now we want to put the positive charge plate here. So however we've been charging the plates, we hook it up to some high voltage device, we just have to flip the switch so that the two plates are now oppositely charged. Now we're ready, and then we have to get a source of protons. Maybe we get some hydrogen gas and we ionize it and pull the protons off. And then we're going to introduce the protons at rest at that place. So what changes? Well, the electric field is the same, but it's oriented in the opposite direction. So the magnitude is the same. These formulas still work. So it's still going to be force is Q times E. The force is the same as it was before on the electron. The force on the proton will be the same as the force was on the electron. If the forces are the same, will the accelerations be the same? And acceleration depends not just on the force, the acceleration depends on the force and the mass. So even though the charge of the proton and electron are the same, and the electric field that they've been placed in has the same value, they don't have the same mass. The proton is 1,800 times heavier. It's got 1,800 and something times more mass, and that says that its acceleration will be much, much less. Now 10 to the 12th still seems pretty fast. When we scale this down to, if we carry out the same calculations as before, by solving for the velocity, look how much slower the proton is traveling when it exits. So it's traveling at, less than 1% of the speed of light, much less, right? Yeah, it's traveling at less than 0.1%, 1 part in 1,000, 8 parts in 10,000. So much slower because of that higher mass. Now what if we send these charged particles through, but instead of sending them, accelerating them to higher speeds, what if we send them through with the initial velocity along the distance between the two plates? Well, if we do this, so we're going to send in a beam of electrons. Maybe we've accelerated them from the previous problem, but now these electrons are going to get pushed to the side. We're going to send them this orientation through the electric field. Well, the electric field is this direction, so the force on the electrons, they're negative, will be towards the positive plate. What that's going to look like is, it's going to look kind of like projectile motion. If you think back to chapter 3, we had projectile motion. We had a cliff and we launched something off a cliff and gravity would curve the path. Well, the same thing's going to happen here. So the electrons are being introduced at a certain speed into this electric field. There is going to be a force, Q times E. There's going to be an acceleration, which is Q times E divided by M. Oh, look, it's the very same acceleration we had before. But this time, there's an initial velocity, and the initial velocity is perpendicular to the E field. So this is what the force diagram looks, it's a force diagram, but it's got V naught and A included. So at, what are the formulas going to look like? So what's going to happen in the x direction is we're going to have constant velocity. We saw this with projectile motion where we had a V naught horizontal off a cliff. So that's what we've got here. And that speed is just going to be maintained in the x direction throughout the whole problem. So this is our Vx throughout. But the Vy, it's going to start picking up speed. It's going to pick up speed in the y direction. So we're going to have to write the acceleration times time. Now I think back in one of those problems, it asked, why is it safe to ignore gravity? And that's because the acceleration due to the electric force is 3.5 times 10 to the 15, and the acceleration due to gravity is 9.8. So yeah, ignoring gravity seems pretty safe, unless we're keeping 15 significant figures in our calculations, which we're not. So we're ignoring gravity because these accelerations are just, they're a million billion times bigger than what we saw with gravity. All right, so here is the 1 centimeter distance that it's traveled, and we can just run a bunch of kinematics. By the time 1 nanosecond has gone by, this is going to happen fast. So we can't let an entire second go by if it's got this kind of an acceleration. So let's scale this down to 1 nanosecond. Well, plugging into my kinematic formulas, the Vx has not changed, but the Vy has reached 3.5 times 10 to the 6th. So within a nanosecond, I've got a y velocity that's starting to be kind of the same order of magnitude as my x velocity. Now, the location, after 1 nanosecond, it will have traveled a distance of 1 centimeter. And so I'm just saying, I'm trying to get an idea of what happens after 1 nanosecond. It will have traveled 1 centimeter in the x direction. How far will it have been pulled off course? And it will have moved off course by 1.8 millimeters. Okay? So it's traveled 10 millimeters forward, and it's curving, it's following that curved path, and it will have traveled 1.8 millimeters off of that center line, and these are the components of velocity it will have. So all of this kinematics looks the very same as what we did in chapters 3, I'm going to say, except that now the force is the electric force instead of gravity. Okay, let's move on. There's another important topic that we want to take a look at here, and it's the topic of dipoles. Now, we mentioned dipoles earlier. A dipole consists, we say that we have an electric dipole whenever we have equal amounts of negative charge and positive charge that are being held together. They can't separate from each other for whatever reasons, and so they're stuck. And we said this is a good example of this might be an atom or a molecule. You know, molecules are going to have certain regions that are positive and regions that are negative, and because of all the other electric forces going on, the positive and negative charges, they're not going to separate. And so we can say that it's a neutral object, but it has positive and negative regions to it. And for the dipole, we use this symbol of P. I apologize for that. I guess there's a P in dipole. So the dipole is defined as the charge, the individual charge of each charge, times the distance between them. Again, center to center. They got it right. Yes, they got the center to center. Look at that. So they're measuring L from the center of that charge to the center here. Why didn't that happen on the earlier slides? I don't know. So that's our definition of a dipole. Now, if I take something with a positive charge and a negative charge attached, they're fixed. They're both built into some other object. And I place it in an electric field. So I'm going to take my dipole, set it in an electric field. The positive charge is going to feel a force in the direction of the field. The negative charge is going to feel a force in the opposite direction. They're both attached. They can't separate from each other. And so instead they rotate. So this object, this dipole, will rotate in an electric field. What we can do is show that there's a certain amount of torque going on here, and the torque is going to vary with angle theta. When theta is equal to 90 degrees, when the dipole is oriented perpendicular to the electric field, that's going to be maximum torque. That's when the forces are going to be trying to really rotate this. What would happen if theta becomes 0? Well, if theta becomes 0, then the torque goes away. So here's the very same diagram right here, and I'm identifying force 1 and force 2. Now, force 1 and force 2 are going to have the same magnitude. They're both going to be given by Q times E, because this is charge plus Q and this is charge minus Q. Now, torques, if you remember, this takes us back to chapters 10 and 11. Torques are given by, actually chapter 11 is what we're drawing this from, by the distance, we're going to call that R1, times the force, times the angle between them. Now, the distance vector, the R, starts at the, I'm going to call this the center of mass, out to where the charge is located. So that's R. The force is off in this direction, so theta is the angle between those two vectors. So if you remember, this was defined in terms of a cross product. And so the torque we end up with is R1 F1 sine of theta. The torque for 2 is R2 F2 sine theta. We can write those out. The total torque, these two torques are working together. Force 1 and force 2 both are creating torques that are tending to rotate the object. Oh, I did lever distances down here. This works too, so you don't have to think in terms of cross products. So this is R1 sine theta is the lever distance, and the lever distance here is R2 sine theta. So that totally works. And so I'm adding these two torques together. I'm going to get R1 plus R2 QE times the sine of theta. That says the torque is equal to, well, R1 and R2 combined is the length of the dipole. So the dipole then is given by Q times L, and I can rewrite the torque as dipole P times E times the sine of theta. So again, if theta is equal to 0, there's no torque. If theta is equal to 90 degrees, that'll give us the maximum torque. And this can also be written as a cross product, so I'm not so worried about that. I think the formula on the left is probably adequate to do what we need to do, but you can write it in terms of a cross product if you want. Okay, so again, if we think in terms of a dipole, we looked at this example earlier, the E fields are surprising, right? The E fields can be in surprising directions, and so using these electric field lines is helpful to see where the electric field would be. So here's an example. Here is, well, let's go back to this other picture. Okay, what we really also want to point out with this is that a dipole, there's going to be two things going on with a dipole. One of the items we just looked at, and that is a dipole will experience a force due to the presence of an electric field. So if I already have an electric field, and I place a dipole into that electric field, the dipole will experience a torque. What this is showing now is not only does a dipole experience a force due to an electric field, the dipole generates its own electric field. So this is showing what would the electric field do to the dipole itself look like. So just like before, we said charges can either create electric fields or they can feel the effects. Dipoles are the same way. The dipole here is creating an electric field. In the previous example, the dipoles were feeling the effects of electric fields generated by other charges. That's what happens with all of these charges. So this is an example of calculating an electric field at kind of a sideways position here. And we kind of looked at this before. It's kind of surprising the electric field is sideways. So this is a calculation. Now, I think, well, we're doing pretty good here. Let's take a look here and see. So here is the dipole. There's the positive charge, there's the negative charge. Here is point A. What's the electric field at point A due to the presence of the dipole? Well, the dipole consists of two charges, and I'm going to say the distance between these, and now before we were saying this is L, but I'm going to break it up into A, and I'm going to center the dipole on the origin of a coordinate system, just to try and be really clear about distances. So the dipole itself is defined as the charge Q times the distance to A, the way that I've defined distances here. So X would be from the center of the dipole out to where point A is located. Now, the electric field due to charge 1, oh no, charge this one. So the electric field due to the positive charge is here. Okay, I'm confusing myself. This is E1, this is E2. These are two distinct formulas. So here's the electric field due to the positive charge. That would be KQ divided by distance squared. Now it turns out that point A is a little closer to the positive charge than it is to the negative charge. And I'm going to keep track of that by saying X minus A for the positive charge, whereas the distance to the negative charge, at least the way I've set up the diagram, is going to have X plus A. That's a plus, not a T. All right, now these are directly opposed to each other, so we can, I wrote this as a plus sign. I guess the convention I've been using is to say this is negative. So I'm going to take E1 and subtract off the E2 that I've calculated. I guess the minus sign is here. So, I mean, that's the kind of stuff you got to do with the diagrams too, is make sure that the minus signs get included, but that they only get included once. And so that's going to show up right here for the E field. And when I calculate, this is the E field at point A. So for any location along the axis, the electric field is given by this expression. Now what happens if X becomes really, 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 really large. If I get far away from a dipole, what would the formula for the electric field become? And when X gets really big compared with A, what we can do is our trick of ignoring A compared with X. So wherever X and A are, wherever they're being added or subtracted, I can ignore the really, really small piece. In fact, it's squared, so it's going to be something really small squared. It's going to be super small. I'm just going to keep the X squared. Now, the X squared is inside another square. That's 4 powers of X. And that says that when I look far away from this dipole, the electric field is 2K times the dipole, which is just a fixed bunch of quantities, divided by X to the third. So as you might expect, let's see, if I have just a point charge by itself, it's positive. Then the electric field drops off like 1 over distance squared. If I have a dipole, at first you might think, well, if I have a dipole, it's not going to have any electric field at all, because the positive and negative signs will cancel. But that doesn't happen. The only way that the positives and negatives will exactly cancel is if they're located at exactly the same location. These are not. They've got a little bit of separation. And that means that the electric field over here, and the electric field over here, and even the electric field here and here, are going to drop off like 1 over distance cubed. Now, cubing the distance, that's a bigger value than squaring the distance. It means that the electric field around a dipole drops off more rapidly. So if I have a dipole, it's not going to influence things over a large distance. Its influence is going to be restricted to shorter distances, more so than a point charge all by itself. Okay, again, we can carry out the same calculation. This one's a little trickier because it's at this perpendicular location. So the electric field values themselves, E1 and E2 turn out to be the same value, but they're not lined up. So in this example, I have to take components. When I do carry out the components, I get a cosine factor. I write in the expression for the cosine. That's adjacent over hypotenuse. But at the end of the day, what we find once again is that the E fields, due to a dipole in any direction I look, are dropping off like distance to the third power. So this is kind of interesting, right? Because again, if we think of this in terms of atoms and molecules, I'm thinking, well, in my chemistry classes, there is the chemical bond that gets set up in a molecule. And the chemical bonds are due to the positively charged nuclei and the negatively charged electrons attracting each other. And that's the electric force holding that chemical bond together. Once that bond has formed, you're still going to have leftover little bits of positive and negative charge. You're going to still have those molecules, more often than not, are going to have leftover dipole effects. And so you can look at, well, how do dipoles attract each other? Because I formed the molecules, and they're very rigid and sturdy and stable, like a water molecule or carbon dioxide molecule. But then I know that the water molecules are going to have leftover positive and negative regions, and so the molecules themselves are going to still attract each other. Not with the same force as a chemical bond, but with forces that are dropping off like maybe 1 over the third power. We'll take a look at this in a little more detail. So this becomes very interesting in looking at properties of molecules. Here's an example. It says there's a water molecule. Now, we can actually measure a dipole of a water molecule as being 6 times 10 to the minus 30 coulometers. And so it's asking some properties on this. Now, you might think, well, wait a minute. A water molecule is not one negative charge and 1 positive charge, and you'd be right. So it's not that simple. When we take molecules, the nuclei can be very well represented as point charges. So there's no problem there. If I look at the nucleus of any atom inside a molecule, representing that as a point charge works really, really well. The electrons are not point charges. It doesn't matter how many diagrams you see in textbooks indicating they are, they're not. So the negative charge on the electrons is spread all over. What we can do though is we can say that the water molecule has a dipole that's equivalent to this much charge separated by this much distance. Turns out if you do the calculations, you find out the water molecule is the equivalent of having a little more than half of a fundamental charge separated by this distance. So the distance we have here is 58 picometers. So, and again, we're not so interested in the details of this as, so we've gone and we've determined how much charge, effectively, how much charge is being separated in the water molecule, and then we can use the formulas for torque. And the torque, you know, it's 10 to the minus 25 newtons times meters. Just, you know, a chance to use the formulas. So here is the water molecule inside that field, and let's look at some numbers on the water molecule. So this is 95.84 picometers, and the opening angle here has been measured at 104.45 degrees. And so here's an oxygen nucleus, here are the hydrogen nucleuses, and they're separated by this distance. I'm thinking those two slides may have been out of order. Oh no, I think we're good. I think. I've got to go back and double check. Anyway, these are the numbers that go along with this diagram. Is it 17? Yeah, you could kind of read these in either order, I guess. Let me see if they've given any numbers on this. They haven't. Okay. Anyway, let's take a look at a water molecule. So here's a water molecule. This is the bond length that we talked about. This is the opening angle that we've talked about. The electron distribution, so I've got these, you know, these nuclei, these point charge, positively charged nuclei that are placed at different locations. And then they're surrounded by electrons that are different shaped probability distributions, and we'll see this when we get to quantum physics of atoms and see what the electron quantum states look like. The protons and neutrons are in quantum states too, but they're tiny. The distribution of those quantum states are packed into a really small package. And so here's a collection of water molecules. And again, what we talked about was this is considered to be a chemical bond. This is considered to be a chemical bond. That's a pair of electrons that where a lot of the distribution is between the nuclei, and it's kind of locking those nuclei in place. I mean, there's still vibrational energy going on, but that's a really stable bond at everyday temperatures. At 300 Kelvin, that's a very stable bond. But the electron distributions leave one end of the molecule with a little additional negative charge and the other end with some positive charge to it. Now, in the problem, they also wanted us to go in and we did the calculation of torque, but just to show how torque works, as a function of angle, this was the formula we came up with. So the torque is given by the dipole times the electric field times the sine of the angle. And then what they wanted us to do was to go in and calculate how potential energy would be affected. So that means that you can wind up these molecules in one orientation and store some potential energy, and we did that by taking the torque and integrating over the distance. In any case, the formulas, the official vector formulas look like this. We're not so interested in the derivations as we are in understanding why the graphs, why the formulas have the pattern that they do. This is the amount of potential energy as a function of the angle. So these are formulas we can work from, go back and forth between the graphs and the angles, kind of reason through what's going on. Just as an example of how water molecules might interact with each other, or any other molecules that have dipoles to them, So let's say that we've got some water molecules here, we have a water molecule here, and we have a water molecule here, and they happen to be lined up to where the positive end of one molecule is closest to the negative end of another molecule. That's going to be an orientation where these two water molecules are going to be drawn towards each other. So these are intermolecular forces. These are not the forces holding the individual molecules together. These are forces that bring molecules together and keep them, well, that's what makes water a liquid at 300 Kelvin. So if these dipole effects were not present, water would be a vapor. H2O molecules would not be drawn towards each other very forcefully, and at 300 Kelvin they would have enough kinetic energy that they would be a vapor like ammonia. Ammonia is a vapor at room temperature, or is it a liquid? Maybe it's a liquid too, huh? So these would be vapor if it were not for these other interactions. So what we can do is we can say, okay, what are the forces holding this dipole together with this dipole in these particular orientations? And orientations make a difference here. So it's, it's a bit of a complicated problem. But what we can do is say, okay, there's four forces going on. The positive here is attracting the negative here and repelling the positive. The negative here is repelling the negative here and attracting the positive. Now I can think of that as how many interactions are there? Well, there's one here, those are both attractive. And then there's one here, and those are both repulsive. So I'm writing down two forces that are attractive. These are going to tend to draw the two molecules together. And if I look at the distance between the molecules, from the center of this molecule to the center of that one, I'm going to label that as R. And so the negative here and the these are the repulsive terms. I guess I'm using those as negatives and these as positives. So I'm looking at the net force acting on this molecule, and there's two repulsive terms, and they both involve a distance of R. Then there's an attractive term between these two, and that is R minus 2A in terms of distance, and there's an attractive force between these guys. That distance is larger. So who wins out? The two forces that are separated by distance R, or the combination of one distance of R minus 2A and one distance of R plus 2A. Now the Q1s and the Q2s, they're all the same. The Q1s and Q2s all have the same values. These are dipoles. And so I've taken these four different forces. We've lined up the molecules to keep this as simple as possible. They're all going to be given by kq squared over distance squared. There's a 1 plus a 1, those are the repulsions. And then there's a minus 1 over 1 minus 2a over r squared, 1 over 1 plus 2a over r, plus 2a over r squared. Now there's some approximation techniques, and you guys are not expected to be even familiar with these. They show up in calculus class, I think, in 3B. So if you've taken a full year of calculus and you've taken Math 3B, you've seen these approximation techniques. Now we do use these in physics very often. If we have something that's small compared with 1 taken to a power, we can do what's called expand out that function and write it as a series. We can write it as a series of mathematical terms. And if u is much smaller than 1, then in this series, 1 is the biggest value. And then nu will be smaller. The next value is nn minus 1 over 2 factorial u squared. The terms just consistently get smaller and smaller. What that means is we can use this as an approximation technique. Now what we find is, if we go back to the problem just before, what we've got are 1 minus 2a over r to the minus 2 power, and 1 plus 2a over r also to the minus 2 power. I want to expand those. The current algebra that we have here is kind of difficult to work with. So what we'll do is, there's one of those expressions, 1 minus 2a over r to the minus 2, and 1 plus 2a over r to the minus 2. Using our approximation formula, this becomes 1 minus 4a over r plus 6 over 2 factorial, 4a squared over r squared, minus, now the additional terms are getting smaller and smaller. And it turns out by keeping the first 3 terms, that's enough to solve the problem at hand. So I'm just going to keep these 3 first terms in the approximation. Remember, this is the biggest term. This one's much smaller. This one is much, much smaller. When I do that, I'm going to get a force formula that's kq1 over q2. I kept that the whole, oh, I see. I was allowing for the dipoles to be different values of q. That works. Okay, so the dipoles don't have to be the same q's. Right, of course. All right. So these are the attractive terms, and now I got to subtract these off. Now what happens when I subtract off the 2, these are the repulsive terms. I subtract off the 2 attractive terms. The ones from here and here cancel the big ones over here. So all the big terms are gone. There are no more ones left. The ones exactly cancel out. And that says the biggest effect of the electric force will not be observed because they're dipoles. And dipoles are partially canceling out the effect. So the biggest effect is going to get canceled out. And then when I look to the smaller effect, the 4a over r squared here also cancels the 4a over r here. It's not r squared yet, sorry. So I have to go to the third term before I see something that doesn't cancel out. So what it's saying is that the force acting between 2 dipoles, it's not going to be at the level of a chemical bond. All of that cancels out. It's not even going to be at the next level of approximation. It's going to be reduced down to this kind of much, much smaller term. And so this is it. The force is kq1 q2 over r squared times minus 24a cubed over r squared. And what that works out to be is, I think that's a square, right? That's not a 3, it's a 2. When I rewrite these in terms of the dipoles, I get the force is 6k, dipole 1, dipole 2, r to the 4th power. So remember, the electric fields were dropping off like the 3rd power of distance. The force is dropping off like r to the 4th power. So these dipole-dipole interactions are going to be much smaller than the chemical bond itself. But they're still electric forces. I know they go by different names. You know, you have dispersion forces and van der Waals forces, and they bring up all these different names. The important thing to remember is they're all based on electric interactions. They're all based on plus and minus charges within the atoms. And so one of the examples that the textbook brings out is, now this happens with all sorts of molecules everywhere, like we were saying. I want to go back to the simpler example. This is holding water molecules together, right? Kind of a hydrogen bonding stuff, which is also a result of positive and negative charges. And here's DNA. So here's a double-stranded DNA, and we know that DNA can open up and then replicate, or it can open up and you can get transcription taking place, and you can generate some RNA, and then the DNA can close back up. And maybe you guys have enough background, or maybe worked in labs where you were opening up the DNA and then allowing it to reanneal by varying the temperature or varying the concentration of different compounds in the media that you're working with. And then if you've taken biology classes much, you're familiar with the hydrogen bonding that takes place. And again, this can be modeled in terms of a dipole-dipole effect. And so what's happening is you're getting these regions of the molecule. You know, here's a dipole set up by a nitrogen-hydrogen bond. Here's a dipole set up by a carbon-oxygen bond. And so we're getting dipoles attracting other dipoles. And it's not as strong as a chemical bond. It's not as strong as the bonds that are actually holding on here, but it's significant. And so many of these join together, hold the DNA molecule together, hold the DNA molecule in place. And then also what's important here is it's not just that anything attracts anything else, it's that specific orientations, if you have a molecule where the shape of the molecule places, you know, one of these dipoles close to another dipole, and then at the same time is matching up another series of dipoles, then you can get these attractions between, this is thymine and adenine, with two hydrogen bonds, with two dipole-dipole type interactions. And then cytosine and guanine have three, and the distances are different. So this is happening not with DNA, not just with DNA, but with proteins too, right? With all of this effort to try and come up with vaccines, for example. Coming up with a vaccine means producing a protein molecule that has a certain shape to it, and at different locations on the protein molecule there are going to be regions of positive and negative charge, and we're trying to get our immune systems to generate a protein that will match. We're trying to find a protein that will stick to those shapes, allowing our bodies to generate that, and then prepare themselves for the possibility of additional protons, additional proteins with that particular shape showing up. So if another protein shows up with that very particular shape, our immune system has generated cells that can either, they're ready to stick, the antibodies are ready to stick to it, or they're, you know, like T cells or whatever, that are ready to mass produce antibodies that can stick to that very rapidly. So all of this, taken any molecular biology stuff, you know that the shapes of molecules and the positive and negative charges going on, the real importance of that. Okay, there's another picture of DNA. I guess we will wrap it up with that. There's the summary. But yeah, that's something to think about. It's all done with electric forces and a little bit of magnetic force thrown into. But all the atomic and all the molecular stuff is being done with electric and magnetic forces holding things together. All right, that gets us through chapter 21. We did make it. There was a lot of stuff. Next class, we will be looking at chapter 22. Not as much stuff there, so we can do this. Chapter 22, we're going to be able to do in just one lecture. In fact, we're coming right back to that. Sorry, we're going to take a break, and we're going to come right back to chapter 22 right in 10 minutes, right in the near future here.